So last time we started looking at the facility location problem, where you have a bunch of possible facilities. You have a collection of clients, and these possible facilities have opening costs, and these clients have assignment costs. And you basically want to open cheap facilities. And assign each client to one of them cheaply. Right? And these two goals of opening the facilities cheaply and assigning the clients cheaply are in conflict with each other, right? If you open all of the facilities, then you can assign every client to the closest facility. That's very cheap for assignment, but very expensive for opening. Conversely, if you only open one facility, then it's very cheap to open, but then some of the clients are going to be far away, and it's going to be very expensive to assign them. And so we talked about an LP relaxation for this problem, where we have indicator variables, yi, which indicates that facility I is opened, and xij, which is an indicator variable that you assign client j to facility I. And with those variables, we were able to specify an objective function. We want to minimize the sum of all the opening costs, fi, together with all of the assignment costs, right? But we had these constraints that you could only assign a client to a facility that was open, right? So in order for xij to be 1, you also need yi to be 1. And every client has to be assigned somewhere. So if you sum up all of the assignment variables for a particular client, they have to sum to 1, because at least one of them has to be 1. And the integer linear programming form of this will also have the constraints that xij and yi are either 0 or 1. They're indicator variables. But looking ahead, we know we're going to relax this. And that means we are simply going to require the xij's and yi's to be between 0 and 1. And so once we relax that integrality constraint, we get a linear program, and we know that that can be solved. Now, where we left things off was, right, that's the straightforward step. Anytime you have an NP-hard problem and you want to approximate, it's very natural to formulate an integer linear program and relax it. And that gives you a very natural relaxation for the problem. But the hard part is rounding. Right? And this is where you have to get creative. And it's actually here that we are going to restrict to the metric case. So the integer linear programming formulation that I gave to you and its relaxation, they apply to any facility location problem. Okay, it's a valid description of the problem. The integer linear program captures the problem, and so the relaxation is a valid relaxation of any facility location problem. But the rounding that I show you is only going to work when we can talk about having a triangle inequality for the distances between the facilities and the clients. Okay? And you have to fill this in a little bit, right? We only have assignment costs between a client and a facility. right? But when we're talking about triangle inequalities, we're thinking of both the facilities and the clients as occupying a common metric space, which means that there are also distances between clients and distances between facilities, right? Which can be inferred from or induced from sort of shortest paths among the client facility distances. Yes? Okay, so we've got this nice metric, and now we're going to think about rounding. And we have two different things to worry about in our rounding. We need to round the xij's, and we also need to round the y's, right? We need to get away from fractionally open facilities, make them fully open. We also need to get away from fractional assignments and create integral assignments of clients to facilities. So there are a number of different algorithms for this. I'm going to show you one of the earlier ones, which goes in two steps. The first step is to do something that's called filtering. And what this deals with is the fact that you can consider the fractional assignment cost for a particular client. For client j, I can write Cj just equal to the sum of xij times Cij over all I. Okay? So we know that fractionally the client is assigned to at least 1 unit's worth of facilities, right? And this is the cost of that fractional assignment. Okay? And from an intuitive perspective, right, if this relaxation is going to work well, this fractional assignment cost should tell us something about the actual assignment cost that we end up with when we do the rounding. Okay? Now, what can go wrong with that, right? We've got some non-zero xij's here, right? Can I just take any one of them that's non-zero and use that as the facility for client j? If my goal is to get something close to Cj as my assignment cost? Yeah?
No, if it was like a really small thing, multiplying a very large Cij.
Right, like we have to worry about the fact that maybe among these many facilities that are sort of candidates, some of them are really expensive, but get tiny fractions of assignment. Right? And so you could still end up with a small Cj, even if some of the involved Cij's are very, very large. Okay? So to address this, we're going to go back to Lake Wobegon, where all the women are strong, all the men are good looking, and all the children are above average. Right? We've used that, we've considered that fantasy before. Right? So the point is that these xij sum to 1. Right? That's kind of what happens in the linear program. So this Cj is a weighted average of the Cij's, right? And what do we know about these weighted averages? What did we use when we were looking at hashing, for example? Well, we used the fact that not everything can be above average, right? And we're going to use that here. Right? It's true that some of the costs may be huge, but they won't all be huge. Okay. So in particular, I claim that at most, a 1 over rho fraction of the xij weight can be on Cij's that are larger than rho times Cj. Okay? So again, Cj is the average assignment cost for this client. So we're saying that only a small fraction of the assignment can go to clients whose cost is significantly above average. Sorry, can go to facilities whose assignment cost is significantly above average. Right? And this is the same Markov inequality argument as we've made before. If more than a rho fraction of the Cij's weight was larger than Cj, then that would by itself contribute a value greater than Cj to the overall average assignment cost. So it can't happen, right? Rings a bell? All right. So we've got some facilities that are too expensive, but there's a bunch that aren't. So we will just drop those candidates. From consideration. Okay. We still have a 1 minus 1 over rho fraction of the weight that can accept connections from this client. Okay. However, this isn't really enough thinking in fractional terms because we want the assignment of these clients to be, so we sort of want 1 unit of assignment of this client, right? We can't only do half an assignment of the client. Notionally, what you can think about is that if we increase all the xij by a 1 over 1 minus 1 over rho fraction, then we get back one unit of assignment of this client. But to make room for that increase, we have to increase the yi's by the same factor. Okay? So actually, the xij's are a bit of a red herring here. What matters is that if we increase the weight of the yi's by a 1 minus 1 over rho factor, then we can conclude that every client still has 1 unit of facilities in reach. Okay, which means that their distance is less than or equal to rho times that Cj quantity. Okay. So we've filtered out the really expensive connections. Okay. We've increased the opening amounts to compensate. And now we can say that every client is assigned to 1 unit of facilities fractionally, and none of those assignments are very expensive. Clear? That's the filtering step, to get rid of the expensive assignments. Now what we're going to do in the second step, the actual assignment step, is we are going to assign every client to one of these not too expensive facilities that are still available to it. But in order to do that, we're also going to have to open facilities. So step 2 is the steps of opening plus assignment. And this is where we're actually going to rely on the triangle inequality. Okay. So what we do is we choose the client with the smallest C sub j. Okay. And remember that he is fractionally assigned to 1 unit of facilities, but we have to make an integer assignment. So what we're going to do is we're going to open and assign this client to the cheapest. Sorry, let me be more careful. To the cheapest facility in reach. Okay, the cheapest one of these facilities that remains attached to it as a candidate after the filtering step. Okay. Now the cost. What is the cost of this opening? it's the minimum facility opening cost among the facilities that this client is considering. And importantly, I claim that this is less than or equal to the sum of FIYI among available facilities. Or let me say in reach facilities. Why is that? Yes?
The right-hand side is like at least some weighted average of like FIs.
Exactly. The reason is that we increased the YIs, so this is greater, that after we scaled them up, we have that the sum of the YIs is at least 1. Right? We still have this particular client is fractionally assigned to at least one facility. Okay? Which means that this is a weighted average. Of the FIs that are in reach. Right? But here we took the cheapest of the FIs that's in reach. And so, of course, the minimum is less than the average cost of opening a facility. Yes? Okay. So again, this relies on the fact that we made sure that everybody is still assigned a unit of facility. We could have, and this works for any client, but now I'm going to show you why we take the closest client. So we had our client J, and our client J was connected fractionally to a variety of possible facilities, right? These are all indexed by I, okay? And we are going to open one of these facilities, and we are going to close all of the other ones because we can only charge the opening that we're doing, right? If we open all of them, then the opening cost will be much more than the fractional assignment cost. But if we only open one of them, then the amount that we spend opening is bounded by the fractional cost. Okay, so we're going to close all the other ones. We're going to have only one of them open. And that means that our opening of a facility is paid for by the fractional objective function. Yes? What's the problem, though, if we're going to be closing all of these other facilities? Yeah? Yeah, those facilities might be needed by some other clients, right? Maybe there's a J prime over here, and it really wants to connect to one of the facilities that we just closed. Okay. So what do we do with that guy? We don't have a lot of options right now, right? We may have just ruined the hopes of this poor client for getting a boba store nearby, right? What should we do to meet the needs of this client? Yeah?
Maybe you can send him to the one that is open?
Yeah, we've only opened one facility. We'll use it, right? So for any other client relying on a closed facility, we will assign it to the one we opened. Okay. So this guy has to go all the way over here. The question is, how bad is that? Okay. So the cost of assigning this other client, J prime, how can we bound it? Yeah?
It's bounded by the distance from J prime to the closed facility plus the closed facility of J plus the distance from J to the...
Exactly. So if I call this facility that I opened I, right, and here's this facility that I closed, I prime, right, the cost of assigning to J to facility I is at most the cost of assigning J prime to its preferred facility, C I prime J prime, right? Plus these other two costs, which involve assigning J either to facility I or to facility I prime. Yes? But now how can I bound these three costs? Well, this is where I rely on the filtering step, right? What does the filtering step do for me? Why did I filter? Yeah?
You got it in terms of row and like the uppercase CJ.
Exactly, right? I have here individual assignment costs, but I made sure that anything, that any non-zero assignment, right, is to a not too expensive, is to not at not too large a distance, that everything is kept in reach, right? So in particular, this one is at most rho times CJ prime, right? That comes from the definition of the filtering step. And both of these involve distances from J to candidate facilities. And so both of these are less than rho Cj. Right? Now, can I simplify this further? How did I pick J? Well, I chose J to have the smallest value of Cj, right? Which means that Cj prime is bigger. And so all of this is at most 3 rho times Cj prime. And this is exactly what I want, right? The cost of assigning J is bounded by something involving the fractional cost of assigning J prime. Cost of assigning J prime is bounded by the fractional cost, the fractional cost of assigning J prime. Yes? And so now what have I accomplished? I took a particular client, I opened a cluster, I opened one facility from a cluster that has one total unit of weight, and then I added in all of the facilities that have that cluster in reach. Sorry, all of the clients that have that cluster in reach. So I've now taken care of a whole bunch of clients, right? This resolves all the clients with any assignment to J's cluster of facilities. Okay. So now what I'm going to do is I'm just going to delete along with deleting all of these facilities, I'm going to delete all of these clients, right? I've made a decision about certain facilities and I've made a decision about certain clients. Now notice that any client that still remains had no weight associated with this facility. So my linear program is still a valid solution for everybody who's left, right? Everybody who's left, all of their fractional assignment is to facilities not in this cluster, right? If they were assigned at all to a facility in this cluster, they would have been taken care of already. Okay, so I can just go back and pick another, pick the next client that hasn't been dealt with, that has the smallest remaining CJ, and apply this procedure all over again. Yes, a question.
The less than equal 3 row CJ prime.
Remember that when I decided which client to start with, I picked the client whose CJ is the smallest, which means that CJ prime is bigger.
Wait, wouldn't CJ prime be larger? Or sorry, wouldn't CJ prime be smaller since you process that first?
No, I chose the smallest CJ, right? So CJ prime is bigger than.
Oh, CJ prime has the okay.
Right, because I didn't choose J prime. And the reason I didn't choose J prime is that CJ prime is bigger than CJ.
Okay.
All right? So does this make sense? Is it clear that sort of after I've done this process for a particular J, I'm all set to begin it for a different J? And so I just repeat this process until I'm done, right? until I've made assignments for every client. Actually, let me just put a note in here. Any clients not assigned have no assignment in J's cluster, which means that all of their assignment is to other facilities which were not closed in this step. So I can repeat this whole process. Until all clients are assigned. Yes?
Is the idea with the, when we threw away the big ones, that just like, it gave us a slightly worse solution to the linear program, like worse by a 1 over 1 minus 1 over 3 factor?
That's right. Right? You could go all the way and say, I'm just changing the solution to the linear program, right? I'm scaling up the yi's and the xij's, and it's still a valid solution to the linear program, right? Its cost has only increased by a 1 over 1 minus 1 over rho factor, but it's still feasible, and so I could round against that. That's not quite the best way to do it, because if you just talk about an increase in the cost of the overall linear program, you're kind of jumbling together the opening costs and the assignment costs. And really what we did here only required us to increase the opening costs, right? So that we still have 1 unit of assignment for every client. Okay? So that lets us talk, that's exactly where I was going. In terms of the resulting approximation ratio, right? We increased all the yi's by this 1 over 1 minus 1 over rho factor, right? And so our overall opening cost is bounded by the sum of, in a particular step, our opening cost was bounded by the weighted sum of the facilities that we closed, right? We only closed each facility once, so the overall cost of opening facilities is at most the sum of the FIs times these reweighted YIs, right? And so that is bounded, that is equal to the fractional opening cost divided by 1 minus 1 over rho, right? At the same time, we assigned each j at cost rho j, or at cost at most 3 rho times cj. So that implies that our assignment cost is at most 3 rho times the sum of cj's. But cj is just the fractional assignment cost from the objective function for item j. So this is at most 3 rho times the fractional assignment cost. Yes? So we can choose rho to balance these terms. Okay. We want 3 rho to be equal 1 over 1 minus 1 over rho, which is just rho over rho minus 1. Okay. And if you solve for that, you find out that you should set rho equal to 4/3. And when you plug that in, you get a 4 approximation to the facility location problem. Okay. So again, in the terminology that I introduced last time, what this shows that the integrality gap is 4. Okay, that there's, whatever your fractional solution is, there's an integer solution that only costs 4 times as much. That also proves that we are within a factor 4 of the optimum, because we know that the fractional solution is a relaxation. And so the fractional solution is better than the optimum, and we're within a factor of 4 of that. Clear? All right. So just a little bit more to say about facility location. There have been a lot of papers on this. As you can see, it's a pretty general problem. It's a kind of a clustering problem, right? You're trying to gather things together and then open a facility for each of them. There are a lot of variants. There are capacitated facility location problems where you're only allowed to assign a certain number of clients to each of the facilities, and lots of other constraints that you can add. So it's seen a lot of research. At present, I think that the best known approximation is a 1.488 approximation to the problem, so significantly better than the 4 that I just showed you. Also, the complexity theorists have shown that you can't do better than 1.463. Okay. So the right number is in there, in between those two, somewhere, waiting for a final project to discover it. Okay. Now, the algorithm that I showed you is based on linear programming and rounding. There are other algorithms based on various kinds of local search, greedy search, and local updates that converge to a nearly optimal solution. But I think it's a very nice demonstration of the power of the randomized rounding technique, where you don't have to think about what the relaxation should be, right? You just do it. You still have to think about how to do the rounding, but you're sort of halfway there from just following the standard relaxation approach. Okay? Any questions? All right. Then for our next example, we're going to do one more example of rounding a fractional relaxation of a linear program. But I'm going to try to show you how even there, we can sometimes just follow a standard a standard approach and not have to think about how to do it. Okay? And so the problem that we're going to look at now is called max-sat. Okay? SAT is the canonical NP-hard problem, right? You've got a collection of clauses, of Boolean clauses. And these clauses are ORs. Over some Boolean variables, which I'll denote by xi's. Okay? And these clauses I'll denote by cj's. And notionally, you want to think about an and of all the clauses. So what we have here is a CNF formula. So this might be something like x1 or x2 and not x2 or x3 and let's say not x3 and x1. Okay, so we have these clauses, and the most obvious question is whether it is possible to satisfy this formula. Can you find some assignment of the variables that makes this formula true? Okay. And in this case, the answer is yes, if I've done the formula properly, right? You can set x1 to true, and that makes the first and last clauses true. Then you set x2 to false, and that makes the second clause true, and then you set x3 to false, and that makes the third clause true. So you can satisfy all of these clauses. Now, if you're given a CNF formula like this, deciding whether it is satisfiable is NP-hard. And that is the NP-hard problem, right? We prove NP-hardness through reductions, where you sort of take one NP-hard problem and show that if you could solve it, you could solve a different NP-hard problem. But if you're going to do reductions, you need one to start with that you know is hard to solve. And the starting one is SAT in most complexity theories. Okay? So it is NP-hard to decide. Now, why am I talking about a decision problem? Like, how can we approximate a decision problem? Well, we can't. However, we can ask, in the real world, when you have a lot of constraints, it's often not possible to satisfy all of those constraints. But we can try to maximize the number of satisfied constraints. And that is the max-sat problem. Okay. And the max-sat problem is, of course, NP-hard as well. Because if you could solve the problem of maximizing the number of satisfying constraints, then you would, of course, know whether you can satisfy all of them at once. And this would solve SAT. Okay. But now that we have a numerical quantity, we can talk about trying to approximate it. So before we get to the linear program, let's try something really naive. What if we do a random assignment? What if we just flip coins for the different clauses? Does that work well, or does it work poorly? Yeah?
This should relatively work well, especially for long.
Exactly. This is a strategy that actually works very well for long clauses, right? Because the probability that you fail to satisfy a k-variable clause is only 2 to the minus k, right? There's exactly one assignment of the variables that doesn't work for a clause. And so there's only a 2 to the minus k chance that you will get it. Okay? And that means that random assignment gives us a 1 minus 2 to the minus k approximation for KCNF. Okay, a KCNF is just one where all of the clauses have k variables. Okay, so if all of the clauses are large, we're in great shape. A simple random assignment will do the job. Unfortunately, if the clauses are of size 1, then we'll only get a 2 approximation. Right? That's sort of the worst case for this simple random assignment. Okay. But we're not going to give up on this random assignment idea. We're just going to try and steer it a little bit. And so now, let's instead think for a moment about integer linear programs for this problem and LP relaxations. Okay. So here what I'm going to do is I'm going to have a variable yi for each clause. For variable I. Right, so yi is 0 or 1 according to whether the variable is set to true or false. I'm also going to have a variable zj for a clause j, which is supposed to be 1 if this clause is true. And so the question is, can we define some kind of integer linear program that captures this? Okay. So I'll do the easy part first. Right? We want to maximize the sum of the zj's. Right? That's just the number of clauses that are satisfied. But what are the constraints that we need to impose in order for these zj's to actually mean what we want them to mean? Yeah?
Zj is less than or equal to the sum of like yi or 1 minus yi.
Good. So the point is we have to look at the literals, the variables in the clause, and think about whether they're negated or not, right? And incorporate that properly. And so I'm going to introduce some notation for that. I'm going to say that we need to look at the sum over all of the variables that are not negated, Cj plus, in clause j. For those variables, I'm going to take yi. And then, for all the variables that are negated, I'm going to take 1 minus yi. Okay? If the variable is negated, then a value of 0 for yi means that yi is false, which means that the negation of yi is true. So 1 minus yi is an indicator variable for not yi being true. Right? And so this formula counts the number of variables that are true in the given clause, right? Or the number of terms in the clause that are true. And so we just don't want zj to be 1 if there are no truthful things in the clause. Okay. And now we add the usual requirement that these are indicator variables. Okay. So I claim that this is an integer linear programming formulation for maxsat. Does everybody agree with that? Just annotate this terminology. So this is variables that are not negated in clause j. And this is the negated variables Okay. And now we do the usual or the obvious relaxation. We just don't make them be integers anymore. We say these can be fractions between 0 and 1. Okay. So now we have an LP relaxation for maxat. Again, the only hard part is figuring out how to round it. Okay. Now, you'll notice that we're working with these variables that are numbers between 0 and 1, right? Now, what is a special kind of number that is always between 0 and 1? Yes? A probability. Okay. And so this takes us to the idea of what's called randomized rounding. So if we look at this formula, right, these yi's, if we think of these yi's as sort of a probability of something being true, of variable I being true, right, then what this formula is measuring is what? If we're adding up these yi's, and each of them is the probability of a certain variable showing true, what is the sum of those probabilities? Yeah?
Expected value.
It's the expected number of true variables, right? So this is the idea of randomized rounding. I have a bunch of fractional 0, 1 variables. Right? I'm just going to set variable x to 1 with probability x and 0 with probability 1 minus x. Okay? If you have numbers between 0 and 1, this kind of randomized rounding preserves expectations of sums of those variables. And remember, we're working with linear programs. Linear programs are weighted sums of variables. So expectations are a really natural thing to try to preserve, right? Essentially, if you do this kind of randomized rounding, every constraint turns into a measurement of an expectation that is still going to be correct, right? A beautiful trick, okay? Now, we are going to do this to the yi's. Notice that we don't actually control, right? The yi's are the variables that tell us how to set individual literals in the clause, right? We can't decide what the truth value of a clause is. That is derived from the y's. So we are going to randomize round the y's, and then we're going to try and figure out what does that do to the z's. And that will tell us how well we approximate. Okay? So let me tell you how well it does. I'm going to define beta k to be equal to 1 minus 1 over k to the kth power. Okay. Why am I defining that? Well, because I'm going to need it later. Okay. And the values of beta k form a decreasing series. Beta 1, right? This is just 0, so beta 1 starts at 1. Then you get 3/4. Then you get 0.704. And you keep going. And as k gets bigger and bigger, what does this converge to? Yeah? Exactly. So notice this is decreasing down to 1 minus 1 over e. Okay. My claim is that under randomized rounding, any k literal clause will become true with probability at least, clause, will become true with probability at least beta k times the z value of that clause. Okay. And again, this is sort of normal and the kind of thing you should expect when you're doing an LP rounding analysis. You try to tie different parts of your solution to different parts of the fractional solution, right? And so what we're saying here is that whatever the zj's are in the fractional optimum, we get at least a beta k fraction of every zj. And as we just said, all of these beta k's form a decreasing sequence, so this is at least 1 minus 1 over e times zj. Okay. Now, if each clause is true with probability 1 minus 1 over e times zj, what can we say about the overall value of our solution? Well, notice that that value is a random number, right? We're randomizing, so we can't say that there's a specific value. But what can we say about this random variable that denotes the number of clauses that we satisfy? Right? Each clause is satisfied with probability, the jth clause is satisfied with probability zj. Right? So what can we say about the total number? Yeah?
The expectation is 1 minus 1 over e times whatever the sum used to be.
Exactly. So if each one is satisfied with this probability, then we can say that the expected number of satisfied clauses is at least the sum of the probabilities that each clause is satisfied. Right? Which we've just said is at least 1 minus 1 over e times the sum of the zj's. Notice I'm abusing the notation here, right? K is actually dependent on j, but hopefully it's clear what I'm saying. Yeah? And why is this a good quantity? Why do we care about this? Yeah? Exactly. Sum of zj is the fractional optimum. Okay. But this is a relaxation, so the fractional optimum is better than the integer optimum. And so we get a 1 minus 1 over e approximation. Okay. Which is better than the 1/2 that we get through the night. And if you think about it, both of the strategies that we've talked about are random coin flipping strategies, right? It's just that I first talked about an unguided strategy where we just use 50%, an unbiased coin for every variable. The linear program gives us better biases for flipping the coins that lead to a better outcome. Okay. Yes? How do we get the beta k? Well, that is related to the question of why is that true? Right? I made an assertion here, which I haven't proven yet, so I'll prove it. And I will also, then we will see where the beta k's come from. Okay? But let's take a break first so that we have our brain cells back for the mathy proof that I need to do.
So you solve the LP first, and then you apply that guideline.
Oh no, oh no.
Oh, diamond push-ups. That's the way. I don't have the kit. I don't think so.
Like this. I think it's in the okay. Wait, what was like the original definition of it? There's like a limit definition.
Going faster.
Wait, the usual definition, like, it's like, I know like the calculus definition, like if you take derivatives, like
You just say it goes faster. It's just the same thing as inserting time. Like, imagine every time you live.
Everybody really wants to get to that proof as quickly as possible. You know, you're all sitting down just waiting with bated breath for the proof. One of these days, I'm just going to bring in some music, and that'll be that. I have to have a little dance party to get everybody moving. Is everybody just too stunned by the amazingness of randomized rounding to be able to get up? I mean, it is incredible, an incredible concept. All right, let's resume. I've turned my microphone upside down, so I guess I should probably start writing from right to left now to counterbalance that, but let's see what happens. I hope that the reason nobody told me they were having trouble hearing me was that nobody was having trouble hearing me, right? Because the microphone did need to be adjusted. So if you have trouble hearing, make sure you let me know. All right, so we need to prove the claim. Okay. So let's look at some k-variable clause. And I claim that without loss of generality, we can assume that there are no negated literals. I use literals to refer to the variables in the clauses because we also have variables in the linear program. Okay. Why is it okay to assume no negated literals? Well, because we do this 1 minus yi thing, right? If you have a negated literal in your clause, you can invert the meaning of the literal, right? You can replace the literal by a different literal that means the negation of that one. And what was yi becomes 1 minus yi, and what was 1 minus yi becomes yi for that new variable, right? So we can assume that we have no negated literals. That means that we're just dealing with these yi's, right? So we round variable I to true with probability yi, literal. I to true with probability yi. And so what is the probability that the clause is satisfied? Yeah?
The product of 1 minus 5.
Exactly. It's 1 minus something, because it's actually easier to talk about the probability that the clause is not satisfied, right? What has to happen for the clause not to be satisfied is that every single literal has to go wrong, right? Every single literal has to come out false, which happens with probability 1 minus yi. And those are all independent events, so the probability that they all happen is just the product. Right? Everybody happy with that formula? So we're interested in how this quantity relates to zj, right? So for a fixed zj, or for a given zj, the question is, how small can this be? Right? We're trying to argue that if zj is large, you have a large chance of satisfying the clause. So we're going to try and minimize this in the worst case. We're asking what is the worst possible case for this. Okay, so you want to minimize this probability, okay, which means that you want to maximize the product of the 1 minus yi's. Now, what's the constraint that you satisfy? Well, we know that zj is going to be equal to the sum of the yi's. That comes from the linear program. Yes? And this is a pretty standard problem, right? You're requiring the sum of the variables to be fixed, and now you want to maximize the product here. And if you do the calculus, it turns out that you want to do this. You set all of the yi's equal. If I set all of the yi's equal, what are they going to be equal to? They're going to be zj divided by k. Okay? Which means, when we plug it in, that the probability becomes 1 minus zj over k raised to the kth power. So this is a lower bound on the probability that a clause with fractional truth value zj ends up true. And we now need to simplify this quantity. So now I will show you that 1 minus z over k to the kth power is always bigger than beta k times z. And then I'll be done, right? And this is why I'm defining the beta k's, is that beta k is what you get as your bound on this quantity. Okay. And I'm going to prove this by picture. So let's consider the value z. Okay, as a function of z, what happens to these two quantities? So beta kz is pretty straightforward. We're interested in z being between 0 and 1, right? So at z equals 0, beta kz is 0. At z equals 1, beta kz is beta k. Right? And so this is the formula beta k times z. Let's do that a little better. Now, what about this other more complicated formula? Well, what is the value of this more complicated formula at z equals 0?
Yeah. 0.
Right. It is also equal to 0. Okay. What is its value at z equal 1? Yeah. It's beta k. So its value is also the same. So its value is the same at z equals 0 and z equals 1. So obviously it's the same everywhere, right? I mean, any engineer would tell you that. Well, it's not quite that simple, right? We need to worry about the middle. Okay. So what we do is we look at the first derivative of this quantity. And that first derivative is what did I say here? Right, is just 1 minus z over k to the kth power. Sorry, there's a k out here because it's a polynomial. Right? No, sorry, the k's cancel. Right? We pull down a k, but it gets canceled out by the division. It's been so long since I last took a derivative. Which is equal to 1 at z equals 0. And you notice beta k is less than 1, so this tells me that the complicated formula starts climbing above the line. Yes? Sorry, a question?
Shouldn't the exponent be k minus 1?
Oh, yes, thank you. Like I said, don't get to the derivatives very often. Okay? But that doesn't change the fact that it is 1 at z equals 0. Right? So it starts out climbing higher than the linear function. Right? The second derivative is minus 1 minus 1 over k times 1 minus z over k to the k minus 2. This might also be wrong, but what is right about it is that it is less than 0. Okay? Which means that at all z, okay, between less than 1. So what that means is that after starting out shooting up, it just bends over. Okay? It never starts curving back up, right? It's purely concave, or convex rather. And that means that if it ever crossed below this line, it would not be able to turn and come back up. So it can't cross the line until it hits at z equals 1. Okay, and so this is the 1 minus, the shape of 1 minus z over k to the k, and you can see in the picture it is always above the line. So that completes the proof. Any questions? So this immediately gives us, as we've already seen, a 1 minus 1 over e approximation for maxat, which is better than a half. But that's not actually the end of the story. Okay? We talked about the fact that when you do the naive randomization, you just flip coins for everything, that this works really well for big clauses, but fails for clauses of size 1. Right? What about this technique, this more sophisticated LP rounding technique? What kind of clauses does it like or dislike? Yeah?
Better for smaller.
Yeah, this technique is better for small clauses, right? Notice that beta 1 is equal to 1. So if you have a stat formula with only singleton clauses, this gives you an exact solution to the optimum in expectation. Right? Now, talking about expected values of approximation algorithms it puts you on slightly shaky ground because you're not guaranteed to get the expected value, right? You're just going to get it in expectation. So sometimes it might be better, sometimes it might be worse. But those are details I don't want to worry about. They take too much time to talk about, right? The fact that you do well in expectation means that if you just try it a few times, you'll probably do fine, right? And there might be a small epsilon factor that you lose. So with small clauses we do great, but we decay to 1 minus 1 over e for large clauses. But large clauses are where the naive algorithm works really well. So let's combine the two algorithms. Okay, now there are different ways you could imagine combining these algorithms, but I'm going to, I've been having fun with randomization. I'm going to keep going with randomization, okay? I'm going to flip a coin to decide to choose my algorithm. And then I'll run it. Okay, half the time I'll run the naive algorithm, half the time I will run the clever algorithm. Okay? What a crazy idea. Okay, but let's see what happens. What is the expected outcome? For clause J. And let's say that clause J has size k. Okay. Well, half the time, it's going to be true with probability 1 minus 2 to the minus k. Yes? The other half of the time, it's going to be true with probability beta k times zj. Right? Now, zj is at most 1, so this is at least 1/2 times 1 minus 2 to the minus k plus beta k times zj. So this is the expected truthiness of clause J when I randomly pick my algorithm and then act randomly according to the algorithm. Okay? So if I want to bound this, I need to bound this inner quantity. Okay? And let's think about those quantities, right? We have two series to worry about. One is 1 minus 2 to the minus k, which starts out at 1/2, and then becomes 3/4, and then 7/8, right? And gets bigger and bigger towards 1. And then we have beta k, which starts out at 1, right? And where did I write down the next beta k value? 0.70, sorry, 3/4. Okay, then 0.704. Okay, so if k is 1, we get 1/2 plus 1, which is 3/2, right? If k is 2, we get 3/4 plus 3/4, which is still 3/2, right? Here we get 7/8 plus 7/10, which I'm not even going to bother computing, but is bigger than 3/2. And basically, at this point, this is really close to 1. And this never drops below 1 minus 1 over e, so all of these other quantities are bigger than 3/2. And so we can come back here and say this is always bigger than 3/2, no matter what k is. And therefore, we get a 3/4 approximation to the truth value, to the truthiness of z, of clause J, which means that overall, the expected number of satisfied clauses is at least 3/4 of the op. Again, by way of the fractional opt. So we take these two algorithms that have respectively a 1/2 approximation ratio and a 1 minus 1 over e approximation ratio, but if we choose one of them at random, we get a 3/4 approximation ratio, which is pretty mind-blowing. Okay? And it has to do with the trade-offs, right? Where one of the algorithms is strong, the other algorithm is weak, or the other way around. So on each clause, we get a good amount of strength. And the randomization lets us put all that together through a big linearity of expectation. Yes?
To pull the ZJ out like that?
Because of linearity of expectation, right? Or sorry, what I did here was I simply said that I can add a zj here because this just makes this quantity smaller, because zj is at most 1. Once it's here, I can pull it out. Okay? Yes?
Is there a way to bias the coin that you flip it to to choose the algorithm based on like, how long the clause is?
Based on how long the clauses are. Yeah, so once you have this insight, there are ways to develop the algorithm so that you're sort of manually doing the biasing yourself, the way that you say. You kind of pick an appropriate, you don't pick randomly between the two algorithms anymore. Instead, you sort of use a weighted randomized rounding based on the relative sizes of the clauses. But this is one of the cases where sort of the randomized story is just much more elegant to tell than the one where you have to carefully think it, right? I'd much rather make random guesses than actually have to think. And that works here. And you don't get better with that careful analysis. You just match what the randomized procedure is doing. Okay? Any other questions? Yes?
When you first introduced randomized rounding, you talked a little bit about the motivation of looking at the integer linear programming as like expected value. Could you go over that part again?
Yes, absolutely, right? The point is that a lot of times when you define your integer linear program, it's full of indicator variables, right? Variables that are supposed to be 0 or 1. So when you do your linear programming relaxation, you get a number that's between 0 and 1, okay? And if you apply randomized rounding, right, if you have a variable of value y, let me say x, then the randomized round of that variable will have expected value x. Okay. And thanks to linearity of expectation, this tells us that constraints involving these randomized rounded variables will still be met in expectation. And this just says, like, you still get a lot of what the fractional linear program gave you as you move to integers, right? And again, that was true here. We relied on the fact, right, in our integer linear program, which is here, right? Randomized rounding meant that the expected value of these left-hand sides was equal to the fractional value of the linear program, right? And that was a good thing because we then related the probability of a clause being true to the expected number of true variables in the clause. Okay? Now, this is also where we lose, right? The probability that the clause was true has this very nonlinear term in it. And that's where we get a divergence from what the linear programming is predicting. And that's why we lose that factor of beta k. And that's why the loss gets worse the longer the clauses are. It becomes more and more nonlinear, right? If you have just a clause that's a single variable, then that expectation is equal to the probability that the clause is true. Okay. All right. Just to wrap up this story of MaxSat, satisfiability is, as I mentioned, this canonical NP-hard problem, the one that got a lot of attention. In a similar vein, there's been a lot of work on the MaxSat problem in terms of its hardness of approximation. Okay. And in a series, there was a long series of results on this, but what was shown by a fellow named Hastad, if we think about three CNF, where every clause has exactly 3 variables, then the naive scheme, where you just flip coins, gives you a 7/8 approximation for MaxSat, right? Hastad showed that for 3CNF, you cannot do better. You cannot beat a 7/8 approximation for 3CNF. So that is a problem where our approximation results are tight. We have the very best possible approximation that you can achieve unless p equals np, and it is achieved through an utterly ridiculously simple algorithm of just randomly picking true and false values. Okay. And these techniques have been generalized to look at CNFs with variable numbers of clauses, but it's messier. to explain what the best possible approximation is. Okay. This work has also been generalized to what are known as constraint satisfaction problems. You can, instead of having a CNF formula, you can think about an arbitrary collection of Boolean constraints and look at trying to solve these more general Boolean constraints. And some of these techniques still apply there. And it's a very active area of research because constraint satisfaction shows up all the time in practice. It's a very nice general framework. Here's a bunch of logical formulas. Find me an assignment that satisfies all of these logical formulas. Very important in artificial intelligence. Okay? All right. So that's pretty much all I want to say about approximation algorithms, which is good because there's no class on Friday. I might talk a little bit more about sort of alternatives to approximation. There's something called fixed parameter tractability, which gives you a way to think about, well, maybe the problem is hard in general, but can I talk about certain instances being easy and get good algorithms for instances that satisfy certain conditions? So that I'm going to look at the schedule and see if I have time for that on Monday. Whether I do that or not, we're going to be soon moving on to our next topic, which is either computational geometry or an online algorithms. I haven't decided yet. Okay? So have a good break. I'll see you on Monday.